C programming careers in 2026, where C is still used and the salaries these jobs pay. Welcome to Gate and Kernel. C is more than 50 years old. So a reasonable question is learning C still useful for a programming career in 2026? If we only look at web development, mobile apps, or AI scripting, C may seem less important than Python, JavaScript, Java, or C#. But that is only part of the picture. C is still deeply used in operating systems, embedded systems, firmware, networking, storage, cybersecurity, compilers, automotive systems, aerospace, device drivers, and high-performance computing. And some of these careers pay extremely well. There is rarely a job simply called C programmer. Instead, companies hire embedded software engineers, firmware engineers, systems software engineers, kernel engineers, compiler engineers, security researchers, and networking engineers. The language is only part of the job. What really determines your value is what you can do with C. 1. There is no single C programmer salary. Suppose two programmers both know C. One writes software for a small microcontroller controlling an industrial sensor. The other works on a compiler for a new GPU architecture. They both use C, but the second engineer may also need to understand CPU architecture, instruction sets, assembly language, compiler optimization, memory models, and parallel computing. Their salaries can therefore be very different. This gives us an important rule: programming languages do not determine salaries by themselves. Industry, specialization, experience, location, and company matter much more. C becomes especially valuable when it is combined with knowledge of how computers actually work. For reference, the average annual wage for software developers in the United States was around $148,000 in recent government data. But specialized low-level engineering jobs can pay much less or much more. 2. Embedded systems. One of the largest traditional markets for C is embedded systems. An embedded computer is a computer built into another device. Examples include industrial controllers, medical equipment, routers, drones, cameras, robots, sensors, appliances, and automotive electronics. These systems may have a small microcontroller, limited memory, limited storage, and sometimes no conventional operating system. Programmers therefore need precise control over memory and hardware. That is where C is extremely useful. Embedded programmers may work with GPIO, timers, interrupts, UART, SPI, I2C, ADCs, and memory-mapped registers. A strong embedded career usually requires more than C syntax. Think of it as C plus microcontrollers, electronics, computer architecture, and inverters. In the United States, embedded systems engineers can earn anywhere from around $80,000 at the lower end to $200,000 or more at experienced and high-paying technology companies. 3. Firmware engineering. Firmware is closely related to embedded software, but it often sits even closer to the hardware. Firmware can exist inside SSDs, network cards, GPUs, motherboards, servers, storage controllers, CPUs, SOCs, and consumer electronics. Examples include BIOS, UEFI, boot firmware, SSD firmware, device firmware, and SoC initialization. Firmware engineers often work directly at the boundary between hardware and software. They may need to understand pointers, memory layouts, hardware registers, interrupts, boot sequences, processor architecture, buses, and hardware debugging tools. In the United States, firmware engineers can earn strong compensation. Median total pay is around $168,000 in some current estimates, while experienced engineers at major technology companies can earn considerably more. The important lesson is simple: C alone is not necessarily a high-paying skill. But C plus hardware knowledge can be. 4. Linux kernel and device driver development. Now we move deeper into the computer. The Linux kernel is still written primarily in C, with assembly used for architecture-specific operations and Rust increasingly supported in selected areas. Kernel development requires knowledge of processes, threads, scheduling, virtual memory, page tables, interrupts, system calls, synchronization, file systems, device drivers, and CPU architecture. A Linux device driver engineer may also communicate directly with hardware. For example, code may read from a memory-mapped register or set individual control bits. This is one reason C fits systems programming so naturally. There is very little conceptual distance between addresses, pointers, registers, memory, bits, and the C code used to manipulate them. Kernel engineers are valuable not simply because they know C. They are valuable because they understand the machine underneath C. 5. Systems software. Systems software provides infrastructure for other software. It includes operating systems, runtime systems, virtualization, low-level libraries, storage systems, networking stacks, database engines, and performance infrastructure. This is very different from ordinary application development. A systems engineer constantly asks questions like, where is this data stored? Who owns this memory? How many bytes are being copied? What happens when two threads access the same structure? What system call does this operation eventually execute? And what is the CPU doing underneath the abstraction? Those questions are closely connected to C. Current U.S. estimates put systems software developer compensation around $164,000 on average, with a wide range depending on experience and company. The exact number matters less than the pattern. Low-level systems knowledge can be highly valuable. 6. Compiler engineering. Compiler engineering is one of the most advanced career directions connected to C. Modern compiler technologies include GCC, LLVM, Clang, GPU compilers, JIT compilers, AI accelerator toolchains, and language runtimes. Compiler engineers may work with C, C++, assembly language, intermediate representations, optimization algorithms, and processor architecture. They need to understand how source code becomes machine instructions. The path is roughly source code, parser, intermediate representation, optimization, code generation, machine instructions. Compiler engineers may also need to understand instruction scheduling, registers, calling conventions, SIMD, vector instructions, cache behavior, CPU pipelines, and GPU architecture. Median U.S. compensation for compiler engineers is around $148,000 in some estimates. But at major technology companies, total compensation can rise far above $200,000. The difference is specialization. 7. Cybersecurity and reverse engineering. C is especially important in low-level cybersecurity. Areas include vulnerability research, malware analysis, reverse engineering, binary analysis, firmware security, kernel security, and exploit research. Why? Because compiled programs eventually become machine code. The path is C, compiler, assembly, machine code. When you analyze a crashed program or investigate memory corruption, high-level abstractions begin to disappear. You may need to understand stack frames, heap memory, pointers, buffers, registers, calling conventions, assembly instructions, executable formats, and virtual memory. This is why strong C knowledge remains valuable in security research. Specialized reverse engineering roles can pay very well, with current estimates placing median total compensation around $176,000. Again, the valuable combination is not simply C. It is C plus assembly, operating systems, computer architecture, and security. 8. Networking. Networking also contains many systems-level C jobs. Software may control Ethernet devices, routers, switches, TCP and IP, packet processing, Linux networking, network drivers, and high-performance servers. At high packet rates, performance becomes critical. Programmers must think about memory allocation, buffers, copying, interrupts, DMA, concurrency, cache locality, system calls, and the boundary between kernel space and user space. C has traditionally been very strong in this environment. A valuable networking engineer may combine C, Linux, TCP and IP, concurrency, and performance engineering. Current U.S. estimates put networking software engineer compensation around $146,000 on average, with senior specialists sometimes earning much more. 9. Storage and database engines. When most programmers hear database, they think about SQL. But somebody has to build the database engine underneath SQL. The same is true for storage systems. Low-level storage engineering deals with files, blocks, caches, pages, memory, disks, SSDs, concurrency, locking, journaling, and I/O. Database and storage engines must carefully control memory and performance. Engineers ask questions like, how many disk accesses does this operation require? Should this page stay in memory? What happens if power disappears during a write? How can multiple threads modify data safely? And how can we reduce memory copying? These are systems problems. And systems problems are where C continues to matter. 10. Automotive software. Modern cars contain enormous amounts of software. Electronic control units may manage engines, transmissions, braking, batteries, steering, sensors, dashboards, and driver assistance. Many of these systems use embedded C. Automotive programmers may work with CAN bus, AUTOSAR, RTOS, ARM microcontrollers, automotive Ethernet, and safety-critical systems. The career path may look like this: C. Embedded systems. Automotive electronics. Current U.S. Estimates place automotive embedded software engineer median total compensation around $168,000. But compensation varies widely. A traditional automotive supplier and a leading autonomous driving technology company may both use C or C++, while paying very different salaries. 11. Aerospace and defense. C is also widely used in aerospace and defense. Examples include aircraft control systems, satellites, radar, communication systems, navigation, real-time systems, and embedded computers. These environments care intensely about predictability, reliability, timing, memory usage, and hardware behavior. That makes low-level languages important. Typical skills may include C, C++, RTOS, embedded Linux, computer architecture, DSP, and FPGA interaction. Current estimates put median compensation for some embedded systems roles in aerospace and defense around $135,000. Some positions may also require security clearances or specialized engineering knowledge. 12. Why the highest paying C jobs are usually not about C. Now we can see an important pattern. The learning path may look like this: C syntax, pointers, memory, data structures, Linux, assembly, CPU architecture, operating systems, kernel and drivers. Then compilers, security, or advanced systems work. As we move deeper, the problems become harder. But fewer programmers can solve them. That is where specialization creates value. A programmer who can write a simple C loop is easy to find. A programmer who can explain why a multi-threaded kernel structure corrupts memory only under a particular CPU ordering condition is much harder to find. Both may write C, but they are not doing the same job. 13. C plus another skill is the real career formula. If you want to build a career around C, do not stop at the language. Combine C with another technical domain. C plus microcontrollers can lead to embedded systems. C plus hardware can lead to firmware. C plus Linux can lead to systems programming. C plus operating systems can lead to kernel engineering. C plus networking can lead to network infrastructure. C plus assembly can lead to reverse engineering. C plus security can lead to vulnerability research. C plus CPU architecture can lead to compiler and performance engineering. And C plus storage can lead to database and storage engines. This is a much better way to think about a C programming career. 14. What should a beginner learn? If you are learning C today, start with the language itself. Learn variables, operators, conditions, loops, functions, arrays, strings, and structures. Then move into the parts that make C especially important. Learn pointers, memory addresses, the stack and heap, dynamic memory allocation, data structures, and bitwise operations. After that, study what exists underneath the language. Learn binary numbers, logic gates, CPU registers, assembly language, instruction sets, memory, caches, and operating systems. Then learn Linux programming. Study processes, files, system calls, pipes, signals, threads, and sockets. At that point, choose a specialization. Embedded systems, firmware, Linux kernel, networking, security, compilers, or storage. C then stops being merely a programming language. It becomes a way to enter deeper layers of computing. 15. Is C still worth learning in 2026? Yes, but with an important qualification. If your goal is simply to build websites quickly, C is probably not the first language you should choose. If your goal is data analysis or machine learning experimentation, Python will usually get you productive faster. If your goal is ordinary enterprise applications, Java, C#, JavaScript, and other modern ecosystems may offer more jobs. But if you want to understand how memory works, how operating systems work, how hardware interacts with software, how processors execute programs, how drivers work, how firmware controls hardware, how compilers generate machine instructions, or how memory errors create security vulnerabilities, then C remains one of the most valuable languages you can learn. And many careers built on that knowledge pay very well. Conclusion: C is an old programming language. But old does not mean economically irrelevant. The important question is not, how much does a C programmer make? A better question is, what kind of engineer uses C? An embedded engineer may use C to control a microcontroller. A firmware engineer may use C to initialize hardware. A kernel engineer may use C to manage virtual memory. A networking engineer may use C to process millions of packets. A security researcher may use C knowledge to understand memory corruption. And a compiler engineer may use low-level programming knowledge to generate efficient machine instructions. They all use C. But the real value comes from the system's knowledge surrounding the language. A strong career path often looks like this: learn C. Understand memory. Understand the CPU. Understand the operating system. Then choose a system specialization. C is valuable because it gives programmers direct access to the foundations of modern computing: memory, addresses, bits, instructions, hardware, and operating systems. That is why C is still used. That is why experienced C-based systems engineers can still earn strong salaries. And that is why, more than 50 years after its creation, C remains one of the best languages for understanding what is really happening inside a computer. Thanks for watching Gate and Kernel. See you in the next lesson.